So let's go on with section 4.3, inferences for dichotomous data. Dichotomous data means binary data. Usually they follows the binomial distribution. So there are usually two categories in the data, like tossing a coin, we can get either head or tail. But sometimes the secondary data is from the raw data, right? If we get a raw data, we can use some rules to convert it into some dichotomous data, like if the value exceeds a threshold or below a threshold, yes or no. So then we can get the corresponding dichotomous data. And it's actually like the sign test, right? The sign test is whether we get a positive sign or negative sign of comparing two values. So sign test is, the data for sign test is kind of the dichotomous data. We can use binomial on dichotomous data, and sometimes we can use a sign test. Let me turn out the pointer. Okay. So to proceed about how to deal with the dichotomous data, how to use the binomial distribution to analyze the dichotomous data. So let's first review our example 2.4 in chapter 2, and then review some about binomial distribution. So in example 2.4, we had a binomial distribution. Remember, we have a 10 observation sample, and for each observation, there's 75% probability to get one of the results. So if we define one result as A and the other as B, so the probability of getting A for each trial is P. And then the probability of getting the other result B for each trial is 1 minus P. And usually we use Q to denote that. So if A is success, B is failure, then success rate is P, failure rate is Q. And the binomial distribution can be denoted as this one, right? And its sample size, P is success rate for each trial. And for tossing coins, P is 0.5. For some other activities, maybe P can be another value. So let's continue. Example 4.6. Let's look at how to obtain inferences from dichotomous data. So let me introduce this problem. A contract for supplying rechargeable batteries specifies that not more than 10% of their batteries should need recharging before 100 hours of use. To test the compliance with this requirement, a purchaser takes a sample of 20, random sample, and finds 3 fail, which means 3 out of 20 need recharging after being used for less than 100 hours. So assess the strength of evidence that the batch is below specification. If it's 10%, should be 2 out of 20 fail, right? So now it's 3 out of 20 fail. 3 is slightly larger than 2, but we want to know if this indicates a bad performance below the specification, or it's just a normal. All right, so first of all, the test is a distribution-free test. We also assume failure time for each battery is independent with other batteries. So these assumptions may not necessarily to be true, because in some experiments, some physical devices could affect each other's performance. But now, for our example, we need to simplify things and use the method to proceed. So let's just make this assumption. And most of the time, these assumptions are general. So the specification indicates that the failure probability is 10% or 0.1. And when we test this hypothesis, the alternative is larger than, right? So it's one-sided test. But somehow, I think our textbook, our textbook write it as p less than 0.1. Actually, this should be less than or equal to 0.1. And then the alternative is p is larger than 0.1. So this time we use p to denote failure rate, right? Not success rate. Usually we like to use the p to denote the a lower rate, whatever it is. For this time, it's the failure rate. For all the quality control problems, the failure rate is lower than success rate. So usually we use p to, we set p as the failure rate. And when p is 0.1, the probability of getting 3 failures, and we use capital P to denote that probability to getting 3 failures out of 20. Or usually we use P lowercase r probability, short for probability, PR. They are the same. Okay. And this should be how to calculate it. It actually should be out of 20, we select 3. Why I cannot use my pen here? All right, let me use both hands. So this is from 20. We need to select 3 as failure, right? And then P is 0.1 to the power of 3. And then Q, which is 0.9 to the power of 17. This is ugly, but anyway, you get this, right? This to the power of 17. So we need to calculate PR using this equation. This is the binomial distribution equation. Okay. Anyway, we can also use the computer programs to calculate it. And that's the p-value based on our sample data. So if we use computer programs, the easiest way we can use is the binom test in R. Let's go to R. So it's binom. So X is 3, N is 20, and P is 0.1. So, oh, sorry, binom.test. 3, 20, 0.1. And then it gives us the p-value of such a binomial distribution. It also returns by default, it returns the 95% of interval. This is the interval of p. So let's get back to this problem. The result is a weak evidence against the null. And or we can say little evidence for performing the alternative. So 95% interval is this value, right? And 0.1 is actually inside this range. This 95% in confidence interval contains 0.1. So this is little evidence for against the null, sorry, little evidence for against the null, which means we should not reject the null hypothesis. So this confidence interval implies that we may only reject the null hypothesis with p-value outside this interval. So given that, two further questions we can explore. What is the power of a test? Right. The test may give us options to reject the null or don't fail to reject the null, but the power of each test may vary. For a sample size as 20, the power 20 is it's a value between a small sample and a big sample. So the result of such a test is somehow powerful, but if we can get a larger sample, it will be more powerful usually. The second question is, how may we use larger samples to make a test more precise? More precise means we can get a shortened confidence interval, or we can increase the power of the test. So the textbook gives the answer through two examples, example 4.8 and 4.9, but somehow we don't extend those two examples in details, and this is not required in our exam. But if you have interest, you can read more about it. And then confidence intervals. So we can use binomial formula or table or programs, computer programs, to get confidence intervals for binomial proportions. And we can use this normal approximation to get a asymptotic result. 95% confidence interval is when z equals plus and minus 1.96. And binomial, remember when the sample size n is large enough and the success rate p is, or failure rate p is small enough, we can use normal distribution to approximate binomial distribution, right? And the mean is the estimated p, right? For our problem, the previous problem, 3 out of 20 fail the experiment, then this p hat, estimate p should be 3 over 20, which is 0.15. In that way, we get the estimated mean, the sample mean. And also the sample standard deviation is np hat, right? N times p hat. So with the standard deviation mean, then we can get a z value and use the z table to look up the probability of getting a certain number of one outcomes out of n observations. So then example 4.7, find confidence intervals for different confidence levels. So let's roughly go through this example, not in great detail, but you can read by yourself. And here's the function in R to calculate the blue text here, to calculate the confidence interval with different confidence level. We still use binom.test and define the number of one outcomes, the sample size, and then the failure rate. And then we need to define the alternative if they are one-sided or two-sided. So for this, we define it as two-sided, less and greater. And then confidence interval, we can change this value here from 0.9 to 0.95 to 0.99. All right. And this binom.test, it's built in the basic R package. You don't need to install any library. You can just open your RStudio and run it. And some interpretations based on this result. So let's jump to next section. the power and sample size. We said that this is not covered in our course. You may read the example 4.8 and 4.9 by yourself. And then let's jump to caution. Let's go to example 4.10. Let's say what should we pay attention to this part? What means a caution? What caution should we pay attention to? So the problem again is not pasted here, so let me introduce it. 7% of UK children give positive skin test to 3 allergens, which means 7% of them are allergic to one of the 3 allergens. And some experts propose that it's because of the climate and cats. And then they say a desert climate country with fewer domestic cats, the children there will get a reduced positive skin rate. To test it, a random sample of 54 children from a desert country with few domestic cats are tested, but only one child has positive skin to all those 3 allergens. Oh, sorry, my mistake. The 7% of UK children tested positive to all 3 allergens, not one of the 3, right? And this time, another country, desert country, 1 out of 54 children is tested positive skin to all 3 allergens. So now we need to test if a sufficient evidence of a lower incidence compared with UK. One is UK is 7%, and the other country is 1 out of 54. So in this problem, the sample size is 54. Number of success or number of allergen is 1, and the null hypothesis is the probability of positive test is of each trial is 0.07, and it's a one-sided test because we want to test if the positive skin rate of the children in the other country is equal to 0.07 or significantly lower than that. So this is how we do it in R. And then section 4.4. Let's learn some tests related to the sign test. And example 4.11, we use the water contents data again. If I remember correctly, the water content data is in example 3.7. Okay, so we have 20 observations. They're already in the ascending order. We want to test if the median is 9. And this is a two-sided test. Therefore, it's binomial. So if we use binomial test to get intervals, usually the interval is about the p-value, the lowercase p, the success rate for each trial. But how can we get the interval of the median using this data? Let's see how we do it. So we can use, again, use this p binom function in R to get the p-value. The p-value is, again, the success rate, or the success rate means, the p-value is the p-value of if the 9 is the median, right? But it's a two-sided test, so we double this value, right? But when we use p binom, we should first calculate the number of items, the number of observations exceeding our hypothesized median. our hypothesized median is 9. So among these 20 observations, there are 3 observations exceeding 9. So this is 3 out of 20. So we use P binom 3, 20, and the probability of each trial we assume is 0.5. There's a equal likely chance we get an observation above 9 and below 9. And this two-sided test, so we use 2 to multiply it. Then we get a p-value like this is very low, so which means we need to reject the null. We can also use binom.test to get the confidence interval. So it's 17 out of 20 is below 9, right? So or 3 out of 20 is above 9. And this time we don't need to double it. It gave us the 95% confidence interval of the P. So our hypothesized P is 0.5, but 0.5 is not inside this 95% confidence interval, which means we probably need to reject the null hypothesis. But how do we get the confidence interval of the median, given this function only gives us the confidence interval of the P? What we do is we can adjusting this value here until the confidence interval of P can contain 0.5. Then this value here is the upper bound of the confidence interval of the median. And then because it's symmetric, we can use 20 to minus this value to get the lower bound of the confidence interval. So how to do it? Because here we have 17 and the confidence interval is above 0.5. Then let's try 16, 15, 14, 13 until we get the confidence interval contains 0.5. Let's do it here. Binom.test. If we have 16 observation below 9, then oh, my typing always have problem. Okay, 16, 20. Binom.test. Okay. 16, 20. So we got a confidence interval still above 0.5. Doesn't contain 0.5. So we need to again try a lower value, 15. Okay, this time is still above 0.5. Then 14. Okay, this time it just contains 0.5 inside this range. So this 14, we can accept it as the interpretation is the 14th observation among the 20 observation sample, because it's in the ascending order. So the 14th is the 14th smallest. So the 14th observation of this 20 observation sample should be the upper bound of the confidence interval of our median with a 95%. Then, because it's ascending, it's symmetric, the lower bound should be 20 minus 14. It should be 6, right? So the 6th observation should be the lower bound of the confidence interval. Let's go back to the observation. The 6th smallest, 1, 2, 3, 4, 5, 6 is 6.6. and the 14th is 8.4. Therefore, the confidence interval of the median based on our sample should be from 6.6 to 8.4. And then that exact confidence interval is this one, from 0.457 to 0. Sorry, the P confidence interval is this one for 14, and also this one for 6. All right. And next, the quantile test. So median is 1/2 quantile, right? 50%. So since we can test the median, we can also test other quantiles. We just need to redefine the p-value using the binomial test in R. But for other quantiles, we can no longer use symmetry feature, right? Because only when p equals 0.5, the binomial distribution is it's a binomial distribution, it's symmetric. When p equals other value, the distribution is skewed. Example 4.12. For a math test, the national standard is 1/4 of the students will get a score less than 40. A school had 32 candidates taking this exam, and then 13 of them scored less than 40. So based on national standard, if 1/4 less than 40 for 32 candidates, should be 8 of them scored less than 40. But now this school has 13 less than 40, 5 more than 8. So then the parents challenge the headmaster if their school performance is below national standard. So let's test if this school performance is below the national standard or just okay. So in this problem, the parameter to be tested is the first quartile, right? Because it says a quarter should be below 40. So the rate is 0.25. Or we use this formulation. We use Q1, Q2, Q3 to denote the first quartile, second quartile, or median, third quartile. We want to test if it equals 40. This test actually should be better to use one-sided test. But anyway, our textbook use two-sided. We can compare the difference between when we use one-sided test or two-sided test. Let's first look at two-sided test. So for R, we can use this binomial dot test, 13 out of 32 and 0.25 quartile probability to get the result. Let's go there. 13, 32 by nom dot test. 13 out of 32. First quartile, it gives us a p-value of the p from 0.237 to 0.594. This range actually contains 0.25, our hypothesized p, right? So we should conclude we cannot reject the null. The school performance is still in line with the national standard. Yeah, this is the result we get. And so conclusion, we fail to reject it using a 95% confidence interval or confidence level as 0.05. So but many parents still concerned, right? So formal tests don't actually prove things. It's just a one-time test. Maybe the school performance is already below the national standards, but this test does not give us a strong evidence of that. Argument for a two-tail test, right? If we do a one-tail test, the result may be different. Let's say we have a one-tail test, so we need to define alternative as greater, right? Alternative equals C greater. So you see, if we use a one-sided test just to test if the school performance is the same as national standard, or the students rate, the rate of students getting less than 40, scored less than 40 is higher than 0.25, then the P confidence interval is this range. 0.25 is not in this range, which means this time we may need to reject the null and favor the alternative. So if it's a one-sided test, the result is different. And I think in this case, one-sided test makes sense, right? So maybe because we don't have a random sample, the randomness of the sample is questionable. Therefore, our conclusion may not have very valid indication. So tests for Q1 and Q3 are equivalent by symmetry. All right. Next, another test that we can introduce, and it's very interesting, Cox-Stuart test. Why do we use it? When we use it, we want to use it to test for trend. For trend means the data should be in time order, and over the time we want to check if there's any trend, if the observations are slightly increasing or decreasing over time. So consider a set of observation, x1 through xn, ordered in time. We separate those n observations in two groups, the early group and late group, based on their timing. An early group and a late group, if n is even number, we use each observation in the late group. If n is even number, so we separate them into two groups with m observations, m is half n, and use each observation in the late group to subtract each observation in the early group. So we can get m differences between the two groups. It's like paired results, paired differences, right? And then if n is an odd number, then we just discard the middle value. We omit the middle value. So still it can be two groups with the same number of observations, and we do the same thing to get these differences. And the signs of the m differences can be positive or negative, right? Because when we use the later half to subtract the first half, it can be larger than it or smaller than it theoretically. So the probability of each sign should be 0.5, right? So it's again a sign test situation. So this is the Cox-Stuart test. We just use another way to create another data set, and by comparing the early observations with the late observations. but it's actually a sign test situation, right? We care about the sign of each differences here. So let's look at an example, example 13. The U.S. Department of Commerce estimates of the average annual mileages of cars and trucks from 1970 to 1983. So these are 14 years. So 14 observations in each sample. Is there a trend of the mileages? So there are two data sets, but we do not compare them with each other. We compare, for each of them, we compare the early data with the late half data. So we test if each of them has a trend. The first is, we need to know that n is 14, sample size is 14, right? M is 7, half of them is 7, because 14 is even number. So we use ith observation of the second group to subtract the ith observation of the first group to get these differences. This is for car. And next we will study the truck. So if we use R, it's yeah, for car, actually every difference in this observations are negative. All of them are negative, so that's 7 out of 7. If we use R, we use binomial test, then it's binom dot test 7 out of 7. And the p-value is very small, which means we need to reject the null. The null is there's no trend. So the result is, the conclusion is, there is a strong evidence of a trend. That's for car. And then for truck, we do the same thing. The 7 differences, actually the first 4 are negative, and then the last 3 are positive. So if we do the binom test, that should be intuitively no trend, right? Binom dot test 4 out of 7. Okay, this time p-value is almost 1, which means we can definitely not reject the null. There should be no trend for truck mileages. But you may observe that all the 4 negative signs are in the first part, and then followed by 3 positive signs in a row, which means there can be 2 trends instead of no trend. Maybe the mileages of truck decreases first and then increase next. So instead of concluding there's no trend, maybe there's a 2 small trend over the time, right? So that all depends on how long do we define the period, right? So there are some comments we can make based on this result. Periodic trends are common, considering things like weather or other factors. And the inferences is only valid for vehicles in this sample. Maybe if we change the sample, not from 1970 to 1983, if we just choose from maybe 1978 to 83, then the result may be different. That leads us to another concern, whether our sample is truly random. If it's a truly binomial distribution, if it's a truly random sample, these signs here should be mixed, should be alternate, 1 minus 1 plus, maybe 2 minus, then 3 plus. then anyway, some plus, some minus, they alternate quite often. But if there's no alternation, but first half are all one sign and the second half are all the other sign, although the total number of each sign are similar, there may be something not random because there's no alternations. So that leads us to a next topic, some tests for testing the randomness of our sample. So far we have always assumed that the sample is random, or in other words, the observations are independent. But how do we know if this assumption is correct? Which means we need method to test the randomness of our sample. So for example, for coin tossing, in the long run, the heads and tails should be about the same. The two outcomes should randomly alternate. If we have 3 samples of 20 tosses like this, first sample, second sample, third sample, then let's first intuitively conclude if they are random. Then H means head, T means tails. The first sample we may suspect because why do we keep getting the same outcome in a row for a long time, and then another outcome for a lot of times? Then so they should be more alternations than this. However, another extreme is the second sample. Each time it's alternate HT is too many alternations, right? This is they alternate too often, too perfectly. So we may also have concern of the randomness of this sample. For the third sample, it seems more random to us. It has some alternations, but not every time. And in reality, if we just toss a coin for 20 times, it's more likely we will get some result like this, right? So we need to use a method a more scientific method to help us determine whether any sample is random, given we have this kind of data. So we introduce a notion, runs. So for example, in the first sample here, we have 3 runs. The first 5 is 1 run, then the next 10 tails is the second run, then the last 5H is the third run. So there are 3 runs in this sample. The second sample, we have 10 runs. No, we have 20 runs. And the third sample is 13 runs. So for 20 observation sample, 13 runs make more sense than 3 runs or 20 runs, right? So runs test is a way to test the randomness of a sample by testing the number of runs of that sample. How often it alternates, actually, right? We test that. And there are 4 key parameters in the runs test. The capital N is the total observations or the sample size. And M is lowercase m is the total heads or the number of 1 outcomes. N is the total tails or the number of the other outcomes. And then S is counting aid. Why is counting aid? Because S helps determine the probability of getting a certain number of runs. How? So if N is odd, if the capital N is odd, then we set number of runs R as 2S plus 1. So in this way, S help us determine the R, help us represent the R. And then S also show up here to help us calculate the probability. So the probability of getting this number of runs is using this equation. The meaning is from n trials, we select m, getting heads. And from the heads, stop to get a tail is this much combination. From the tails, stop to get a head is this much combination. So we add them up. So there are this much combination of having m runs in a sample. This is the probability of having r runs. And if n is even, then things are simple. We can just double this rate. The probability of getting r runs is this much. So this is theoretically how we calculate it. If use r, we can use runs.test. It can be from different packages, depend on your R version. So for my version, I need to install this package, run the tests, and then use the library run tests, and then the data, we can define it like this. Here, the data is numeric, so it should be a value, a numeric value. If it's head or tail, we can define it 0, 1, 0, 1. And then we can run this. Or some other version allows you to install snpar, this package. So you install.package this, and then library this, and then use the same function runs test. The difference is for runs test in this package, we cannot get exact p-value. All the values are asymptotic. But for this package, you can define exact as false to get the exact p-value. Okay, approximation. Because of the computational complexity of the equations here, right? These are the equations to get exact p-value. To simplify, we can get asymptotic results. So if you use R, the default result is asymptotic. If you want to have exact p-value, you need to use the runs.test function from the snpar library and then define exact as false. All right, let's look at example 14. For the coin tossing problem, suppose we have the 3 runs shown on the earlier slide. We have 3 samples, 3 runs, 20 runs, and 13 runs. Let's test each sample's randomness using runs test. So, which means R equals 3 for the first, R equals 20 for the second, and then R equals 13 for the third. And then we can get these results that is in line with our intuitive guess, right? The first 2 samples have very bad p-value, very small p-value, which means they are not random. The third one is more likely a random sample. We can also use table or software to get exact result and asymptotic result. If we use R to get exact result, the runs test should be from the snpar library. So the testing results verify. The testing result of this asymptotic and the exact should be very close, like this. So the coin tossing is a binomial distribution. Each trial is Bernoulli, right? Each trial may have only 2 outcomes. How about more outcomes? Can we also test the randomness of such a sample? The answer is yes. We can also use randomness test to test the samples with multiple results like this. Example 15. Suppose we have 17 observations with 4 possible outcomes. Maybe it's your grade, right? If we have 17 students, they may get A or B or C or D for their final grade. So 17 observations with 4 possible outcomes. Let's test the sample randomness. So sample size is 17. And then number of outcomes K is 4. We use N1 to N4 to denote the number, the total number of each outcomes in this sample. Then we have 7 runs, right? This is 1 run, then 2, 3, then 4, then 5, then 7. We have 7 runs. And this is a one-tail test, either random or not random. So then please read this example by yourself. It gives us the result like this. So if you use R, the things you can do is you can define data, separate each of them using a comma, but your data should be numeric. So ABCD should be changed to 1, 2, 3, 4, so you can get the same result. All right, we'll skip angular data. It's an interesting topic, but we do not test this part in our exam. Then let's summarize the field of application and what we have learned. So we have, let's first summarize the methods. We have introduced several methods in this chapter. Kolmogorov test is for matching samples to distributions. We have learned it in detail. And Lilleford test is for testing normality. So does Shapiro-Wilk test. These two are not required in our exam. You need to know their concept, their rationale. Then we introduce Cox-Stuart test. Then we learned the inferences for dichotomous data, mainly using the binomial test in R. Then we introduced some tests related to sign tests, including the quantile test, still using the binomial test in R. Then we introduced the Cox-Stuart test for trend. Then randomness test for testing the randomness of the sample. And then we skip this part. And here are the fields of applications for each of the methods, right? The Kolmogorov test in R, we actually use the KS test. So let's say, yeah, this Kolmogorov-Smirnov test, KS.test. And then for Wilcox, not Wilcox. So the applications, biology, KS test, heart weights with or without drugs. And then forestry, Shapiro test, timber volume. And for randomness test, there are a lot of applications. For example, the time-dependent responses, coin tossing, or any binomial distributed data set, we can use randomness test. And then trend test, the pollution levels, we have time series data over years, so we can always use trend test. For those data, we can separate them into two groups, early one and late one. We can also separate them into multiple groups and compare each two of them to see the trend in smaller periods, in shorter periods. Genetic ratio defined tested. Also, it's a quantile test or binomial test. Comparison with standard Kolmogorov test. For example, the some exam passing rate or matching if the distribution of students' grade is normal, then we can use Kolmogorov or Lillefer. And then portion test, testing experiments, what is the portion of to get a certain result. We can use the portion test. Again, we can use the binomial quantile test to test this one. Multiple choice exams, right? The rate, the probability to get one answer, A, B, C, D. So it should be 0.25. And then we can test which number we can get the most. Usually, based on my experience, if you don't know which to select C, you will have a higher rate here. All right, that's all for chapter 4. And these are the homework problems. 1, 2, 3, 4, 5 problems, but 4 of them are just the regular points. One of them is bonus point. I don't specify which one. The thing is, if you get all 5 correct, you will get 2 extra points. The 2 extra points is just the 2 points added to your final score. And then if you get 4 right, then you get just the 4 full credit, which is 10 points of your final score. So if you only get 3 correct, then you get 8 points. So it's like that. All right, and that's all for this lecture.